So moving on. So just a quick flash review of StatMech. Okay. So we recall that these are our four molecular modes of motion: the translational, the rotational, the vibrational, and the electronic. Okay. So we recall that the energy levels of the electronic, so if let's say this is energy level 1, 2, 3, 4, 5, etc. Okay. They get closer together as we go higher up. We're going to prove that mathematically. And the energy spacing for a typical electronic transition, I'm just going to give this in terms of electron volts. This is about 1 to 10 eV. Okay. And so if you remember that 1 electron volt, right, that was 1240 nanometer, that's IR. But 10 electron volt, that goes all the way up to 124 nanometer. So we'll see that that's going to really predominantly span the visible and ultraviolet range, are the predominant ranges that spans. Okay. And so now, I'm not sure. And if you recall, if I were to zoom in on this very first energy level, this first electronic energy level, that small little box here would then correspond to like the entire vibrational energy spectrum. Okay, so we would get now a whole host of levels. So, oops, let's suppose I miscopied this. So level 1 is down here, and then 2 and 3 and 4 and 5, etc. Nope, I'll take that back. Whoops. I missed a whole bunch of lines here. So we recall the vibrational levels are evenly spaced. So there was a whole bunch of missing lines there. So that'd be like level 1, 2, 3, 4, 5, etc. Okay. And a typical value, a typical energy spacing for those vibrational levels will be more like 0.1 to 1 electron volts. Okay? So definitely in that IR region. Okay? And again, these are just general cases, right? And if I were to zoom in on that very first vibrational level, we would see a whole host of rotational levels. And once again, I'm sorry, folks, I'm just realizing how badly I miscopied these diagrams. So these diagrams aren't accurate, but that's okay. For now, all I'm doing is just reviewing what our typical energy spacings would be. Okay. So for the rotational energy levels, a typical spacing is going to be on the order of milli-electron volts. So something like 0.001 electron volt. And that puts us into the microwave regime of the spectrum. Okay? And then recall the translations here, that those levels are so finely spaced together that they make what we call the continuum. Okay? Continuing along in our review of statistical mechanics, so recall the Boltzmann distribution, okay, which says the number of particles in state I divided by the number of particles in state J equals, let's all use the E raised to the power negative EI minus EJ, so the difference in those energy levels, all divided by K Boltzmann T. Okay, and then the whole quantity is negative, right? And so if we remember here, the higher the energy of a state, the lower its population. Okay, so the electronic states, right, we recall that everything is in the ground state in the electronic state because it's got such a high energy state, there's not enough energy at room temperature to populate an upperlying electronic state. Okay, the higher the temperature of a state, the lower its population. Okay, or really I should say the higher the temperature of the state, the more likely a higher energy state is populated. Okay, so some reason I copied that incorrectly. So the higher the temperature of a state, the more likely a higher energy state is populated. So as we increase the temperature of a material, it can excite or it can get into higher levels. Okay, and of course more states are populated if they are closer together. So that's like the translations, right? They get really finely crunched together. Okay, so if we were to look at 0 Kelvin, hopefully remember at 0 Kelvin, everything will be in the ground state. So this kind of shaded area represents 100% of my particles. Okay. At 298 K, there's some type of distribution. Okay, and that distribution might look something like this. Okay, it's going to have a Boltzmann distribution, right? So there's going to be some curve, right? And I kind of drew this curve on its side, but we recognize at 298, of course, depending on if we're talking about electronic, rotational, or vibrational, this is what the populations will look like. And this figure that I've drawn here is a good example for the vibrations as well as the rotations as well as the translations. Okay? The vibrations, the rotations, and the translations will have some kind of distribution, mostly the rotations and the translations. Recall the vibrations, like 99% of everything is in the ground state, and maybe 1% of everything is in the second highest state. Okay? So actually, I'll take that vibrations off the list there. Okay? Getting back into the saddle, folks. Getting back into lecturing. And if such a temperature could exist infinite Kelvin, then all of these states would be thoroughly populated. Okay? Get out of there. Remind me later. Okay. And so another way we can kind of think of this postulate number 2 that I did a bad job describing, the higher the temperature of a state, so as we increase this 298 K temperature, what we would see is this distribution. So let's say the most populated state is state number 3. If we increase the temperature on this system, then the highest populated state is going to move up to upper levels. That distribution is going to shift up to higher levels. Okay? But again, big thing to recognize here, the Boltzmann distribution, and I'm going to put a proportionality sign, E to the negative energy, and I'm just going to write that out, divided by K Boltzmann T. So I want us to be able to recognize when we see something is based off of Boltzmann. And when we see that something is based off the Boltzmann distribution, we should recognize that we're not really talking about a single particle. We're talking about a large number of particles, right? That's what the Boltzmann distribution is all about. Okay, so a nice little review here on the electromagnetic spectrum. Okay, so recall, visible light occurs over a very narrow range of wavelength between 700 nanometers to roughly 400 nanometers and goes as Roy, G, Biv, right? Red, orange, yellow, green, blue, violet. Okay. If we go to higher energy from the visible, we get into the ultraviolet, about 10 minus 7 nanometers. Okay. And if we keep going, we get into this region called the vacuum ultraviolet. And the reason why that's called the vacuum ultraviolet is because these wavelengths will ionize oxygen as well as nitrogen, mostly oxygen with 100% quantum efficiency. So to use this type of radiation, we typically need it to be under vacuum because oxygen will absorb all of that radiation. As we keep going, we get into X-rays. Okay, and notice here that under X-ray, we get core electron excitation. So that's some pretty high energy stuff. And we're going to call this, we're going to note that this corresponds to X-ray, photo, electron spectroscopy. We're going to learn about that type of spectroscopy as we go. Okay? And we're not really going to go any past X-rays, though you notice here if we got into gamma rays, we would be getting into nuclear excitations. Okay? Backing up here, back to the visible, okay, notice here that's referring to electronic excitation, and of course that electronic excitation also extends into the ultraviolet and the vacuum, okay? So really that's related to electronic transitions. So as we go less in energy and bigger in wavelength from the visible, we get into the near IR and then into the far IR, and those correspond to molecular vibrations, okay? And as we go into even lower energy, we get into the microwave, and that corresponds to molecular rotations. So this semester, we're really going to be hitting this hard, going after these molecular modes of motion and their corresponding region on the electromagnetic spectrum. Okay? Beautiful. Carrying on.